assignment is due. The first one is graded, and you can pick it up at the end of class if you handed it in as on a piece of paper. If you hand it in digitally, I think Alejandro's email went back to you. So thanks Alejandro for doing that in a timely fashion. All right, so the next assignment is due today, and Pump to 3 I'll be posting later. Yeah.
So it's kind of like a new question. Can we please probably submit the assignment sometimes at 11:59, because I would like to because of those questions are crazy. So it takes time. So I don't know if perhaps you can help us. Probably if we want to submit funny paper, that should be fine.
Well, I tell you the truth. I've been teaching for 30 years. This is life. And, you know, I'm 29, I don't want to exaggerate. And this is what it takes. To get a graduate degree in physics is work. Now, you know, we have a lot of material to cover. My goal here is not to work you hard just for the sake of working you hard. I have no interest in that. My goal is to do my very best to provide you the tools you need so that you can become an expert in this material at the level that I think is required to get a graduate degree in physics. And so, you know, this is the big leagues, and it means that there's a new level of challenge that's here, and I'll do my very best to help you if you have questions, help you to be able to work those problems if you're stuck in places. But this is what it takes. You know, at the same time, you do what you can do. And, you know, the ultimate final grades are not that tough. You know, I understand that you have many other responsibilities. It's not just Physics 511, taught by Professor Deutsch as one of the sharpest stressors. You got other things to do. You have other classes, you have TAing or maybe research assignments, and you know, you're gonna have to balance your time, and you may not get it all done. You do the best you can. I'm here to help you. But I'm gonna present you the problems that I think everyone needs to do to get up to speed.
Yeah, I never complained about the question. Yeah. I'm just talking about the time frame.
Yeah, but we have only so many. It's all about the economics of the time. So we have a certain amount of material we have to cover through the semester. And so the problems have to come in order to be able in order for us to be able to get the practice we need and the learning that we need on the subjects that we just did. So if we don't do that, we won't cover all the problems that need to be covered. Yes?
This issue now is with the team. If perhaps we can submit the assignment 11:59 of today, if probably we are able to submit the hard copy by 5 p.m.
Yes.
So if you can send like an e-copy to the TD by 11:59 before today runs out.
Oh, sure. So, I mean, okay, so we can talk about that. When should the problem sets be due? Okay. I'm happy to try to adjust. However, the problem is we're going to have them due in a way that things don't snowball, right? I mean, if we say, okay, I need an extension on this, the next problem set will come, and then you'll be behind, you know. So if we want to say, and I'm fine with this if Alejandro is fine with this because it's his time too, that we can say instead of 5 p.m., that, you know, they have to be, you know, by 11:59 p.m. on Thursday, I'm fine with that.
Yeah, that's fine. Why me?
If that's okay, that doesn't change anything.
Thank you.
That is totally fine with me. Again, my goal is not to make this painful for you. I try. It's really not. That's not the point of this. If I could teach this material without grading you at all, that would be my biggest joy. I really am here to do my very best to share my knowledge to the best of my ability with you. That's what I love doing. I love trying to understand things and to share that information with you. It's also my job to grade you. I hate that part of the job, but that's kind of, you know, goes with the territory. Yeah. All right.
ED.
Yeah, all right. Woohoo! Let's get started on this. All right, so last time we were talking about Green's theorem. So Green's theorem we use to solve the following problem. We have some volume V bounded by some surface S, and within that volume is some charge distribution, okay? Static charge distribution. And the goal is to find the electrostatic potential inside the volume, not anywhere else, just inside that volume. And what you're given is two things. You're given the shape of, well, three things. You're given the shape of the volume, you're given what the charge density is within that volume, and the boundary conditions, okay? And that's solved using Green's theorem. So Green's theorem is a theorem of vector calculus, but it is the solution to the Poisson equation with boundary conditions, okay? So the Poisson equation is a difference equation. To solve a differential equation, you always need boundary conditions. This one solves this in a finite volume of space, typically. And here's the solution, formal solution. The formal solution is you convolve the charge density with the Green's function, where the Green's function is the solution for a point charge located at some point x prime. So that's the Green's function is a solution to this problem with certain boundary conditions, because again, to solve a differential equation, you need to know what the boundary conditions are, otherwise you don't have the solution. And then, in addition, there is these boundary terms that are determined by what the potential is on the surface and its normal derivative, okay? So that's the formal solution to the Poisson equation in a volume with a surface that bounds it. And what we also showed at the end of last lecture is that the solution to this problem is unique if you're given the boundary conditions. Given the charge density, once you know the boundary conditions, there's one and only one solution to that problem. Those boundary conditions can be specified differently. You might specify only what is the potential on the surface. Those are called Dirichlet boundary conditions. Or you could specify the normal of the gradient, which is what is the electric field in the direction of the normal, or the negative of it, everywhere on the surface. So I can specify this everywhere, that's called Dirichlet boundary conditions, or I can specify this everywhere, or I can have mixed boundary conditions where at some points on the surface I specify this, and at some points of the surface I specify that. But I can't specify both of these together because that's an over-constrained solution.
When we talk about boundaries, do
Yeah.
we count infinity
We
as
do.
a boundary? Okay.
Yeah, so we'll talk about that in just a moment, absolutely. So, and so, yes, indeed, that's an important point. So, you know, last week or the week before, God, what is time anymore? We solved for the Green's function using Fourier transforms, right? We went to the reciprocal space, and then I said, yes, reciprocal space, and the derivative is algebraic, and we solved it. But now I'm saying something a little bit different. And what's different about what I'm saying now compared to what we did some few lectures ago? What's different is I wasn't very clear necessarily as to the boundary conditions that we were implicitly assuming when we solved for the Green's function using the Fourier transform. And it goes to your question. So, you know, if I have a charge distribution and I have no other boundaries that I'm considering, my boundary is at infinity. Okay? So this is the problem in free space. We would naturally, there is no natural boundary to put on the system, so we would take the boundary at infinity, and the boundary condition is that this on the surface is zero, that the potential is zero at infinity. And there we found that the Green's function was our familiar electrostatic potential of a point charge of unit magnitude located at position x prime, okay? But the more general solution to this equation would be this as the particular solution, but then there's a homogeneous solution. So I can write the general solution as this plus some other function that I specified that helps me to satisfy the boundary conditions such that this satisfies Laplace's equation. This clearly is also a solution to this equation because del squared on f is 0. So I can add to our familiar solution, which we might call the particular solution, this homogeneous solution, any other thing that satisfies the Laplace equation, and that will also be a Green's function. And we choose f to satisfy the boundary conditions. So in the case of free space, we chose f to be 0 because that satisfied the boundary conditions. But if we want our system to satisfy different boundary conditions as we have in the problem at hand, where we have some kind of bounding region, then we would choose f differently. What we can understand what that is that inside the region of space, there can be electric field or electrostatic potential due to other charges that are outside the region, because we're not asking us to solve what the potential is anywhere other than inside the boundary. And in particular, there might be surface charge density here. And the potential inside here, due to these charges, will satisfy Laplace's equation, because the charge density is always 0 inside here due to this charge, okay? So what the Green's function does is mocks up the potential due to all the other charges that are creating a potential inside my volume that we're not including in this. We'll see this more clearly in a moment. Okay? Yes?
Basically, are you saying that it's a local equation, and I take a volume, and I solve it locally?
What I'm saying, well, it's not quite a local equation because the Green's theorem tells us that the solution at a local point depends on what it is over the whole surface. But what I'm saying, Green's theorem is a way of, by uniqueness, mocking up the effect, as will this become clearer, of what other, I mean, if the charge, in reality, charges are always localized in a finite region of space. So this is the Green's function in reality for if I included all of space. However, if I divide up space and say I'm only interested in a volume V that is finite, then I can take it into effect what these electric fields do inside this volume by just knowing something about the surface.
So basically,
And this F function is the potential due to these charges, and the reason that it's 0 is that the right-hand side of the equation is rho at the positions of interest, and these charges outside here are never inside this volume. So the only time the right-hand side of the equation is non-zero is at points where the charge is non-zero. All right, let's continue and think about what we were talking about, where these kinds of problems are most prevalent. And that's when we have conducting boundaries, okay? So let's just remind ourselves about conductors, okay? So a conductor is a material with mobile charges that can respond to the forces. They're unbound. Now, to really, of course, talk about, you know, the real details of a real material is complicated. And we'll talk a little bit about this, you know, when we talk about dielectric materials and so forth. And we have to think about what is sometimes called the macroscopic Maxwell's equations, because you know, the microscopic constituents are atoms and molecules and solids, and, you know, we have a kind of macroscopic description in the sort of statistical physics perspective, whereby we look at things at a microscopic scale and we kind of coarse grain over, you know, Avogadro's number of stuff. But we're not going to go there, okay? To start, we just think about the most ideal case, and if we have an ideal conductor, then we have a infinite conductivity. That means they're completely free to move with respect to any force, and there's nothing holding them back. There's no resistance, because that's futile. And so, stupid dad jokes. Anyway, all right, so when we have such a system, what that means is if there's a force, the thing will move unimpeded, no drag, no resistance. And so in electrostatics, what happens is the charge will just ultimately move until they can't move no more, okay? Because they will move unimpeded in a perfect conductor, okay? So for example, what that means is that, let's say I have a external electric field. Let's say I have a parallel plate capacitor of the kind we've discussed. We didn't really call it a capacitor, but I have, and I put inside here a chunk of material that's a conductor. What is the electric field going to do? Well, whatever, if there would be field lines going from positive to negative, and they're going to push on these charges, and the charges will move in such a way that until they can move no more. And they move no more when there's no force on them. And there's no force on them when the electric field is zero. So what this means is that the electric field inside the conductor will be zero. And the only way that can happen is if there are charges that are accumulated on the surface. They have to move to the surface in order to screen out and cancel the electric field inside here. So that's what happens in equilibrium. Once this will set down, and so the electric field lines will go, you know, like this. With the electric field being zero inside and there being surface charge density as a function of the surface. And it will adjust itself however it needs to adjust itself such that the electric field is zero. Because if the electric field wasn't zero, it would keep moving. And now the only way, so that's what happens, right? So we have the basic facts of a ideal conductor is that the electric field is zero inside. There is surface charge. And how would I find that surface charge density?
It would be related to the field generated by the parallel plates.
It is, and exactly how is it related?
Something like images?
Well, we'll come back to the message of images. But if I told you there's no field inside the conductor, and there's a certain electric field outside the conductor, then there is a discontinuity at the surface. And what determines that discontinuity?
Surface charge.
The surface charge, because we have the boundary conditions, and maybe we remember that, maybe we don't, but the surface charge density says that the surface charge on the surface at that point is equal to the discontinuity in the normal to the electric field at that point, right? So that's equal to the normal component, okay? So there will be a component of the electric field outside the conductor, which is in an external in an external electric field that is perpendicular, is normal to the surface. What about the parallel component, the component along the surface? It has to be zero. Why? Sorry?
Oh, it's continuous. And then
It's continuous. But we don't, maybe there was a tangential point here. But if there was a thing, it would move around, and it's not moving anymore. The only reason that it's stuck here is that it's bound to the surface. That's the only force that we allow on the conductor, is that it's not photoactive, it's not pulling charge off of it. They're bound at the surface. That's the only thing not. If there was any electric field along the surface, it would move. And it ain't moving, because we said, this is the time where it's not moving, it's static. So the parallel component of the electric field is 0 at the surface of the conductor. Okay? And what that also tells us that the electric field is only perpendicular to this, that the surface of the conductor is an equipotential. Why is that? Equipotential means that the potential, the electrostatic potential is the same everywhere on the surface.
Will it work if we move along the surface?
Right, because the gradient along the parallel direction is the electric field. Right? So that is what, and we know that there is no electric field along the tangential, so the electric field is perpendicular to the surface, and the electric field is perpendicular to surfaces of the same potential. Therefore, when you put, a battery with a wire connected to a conductor, it's at the same potential as the top of the battery. Okay. So those are the very basic properties of ideal conductors, and real conductors are pretty close. I mean, a typical metal, copper, etc. It has pretty darn good conductivity, and for all intents and purposes, this is a good approximation to real metals. Okay, so now we come to an example that Donald was predicting, which is the method of images. But let's start with the following problem. So let's say this is a standard problem. You probably had it in an undergraduate. I have a grounded plane at z equals 0. Okay? So I have a grounded conducting plane at the xy plane at z equals 0. Okay? And I have a point charge that is some distance d above the conducting plane. Okay? Now, if I were to sketch what the electric field is in this situation, it would look like the following. We know the electric field at the surface of the conductor, which in this case is at phi equals 0 at this point. It's a constant potential, but we've chosen it to be 0. We could have chosen it something else, but for the moment we'll choose it to be 0. Would look like this. Assuming it's a positive charge, right? So we know that the electric field at the surface of the conductor is perpendicular to the surface, which means that it only has a component, in this case, in the z direction. It has no component, x or y component at the surface, okay? How would I find the electrostatic potential of that? Well, one way to, if we knew, so what we also know is that we're going to induce surface charge on the surface of this conducting plane, right? This is coming out of the board. Everyone understands this is a plane. And we're going to induce negative surface charge. That's where these things terminate. And if we knew what that surface charge density was, we could integrate over all the surface charge density plus this to find the potential everywhere, right? But we don't know what that surface charge density is. At least we don't know it right yet. So we can solve this using Green's theorem. Yes?
So we're gonna have a surface charge density out there. Are we assuming that we're disconnecting the ground connection from it so that we can develop a surface charge?
That's right.
Okay.
That's correct. And we know it has to, right? Otherwise, it couldn't maintain a constant potential. So instead of actually calculating all the surface charge density and then finding the potential as a superposition of the potential for the point charge plus all the surface charge densities, we use the trickeroonies associated with Green's theorem, okay? Technical term. So this comes again to the question, what is the bounding surface? Where do we want to know? So our goal is, okay, so first question, what is the potential below this?
Is it just a plate? Or
It's a plate. This is just a plane. I'm not good at drawing perspectives coming out of it. It's an infinite plane.
It'll be zero,
Will be zero. Why is that?
because it's, all the electric charge is caught up on the plane, it can go past it.
That's right. And we can see that also from Green's theorem. Let me make a hemisphere that has some radius that will go to infinity, okay? And at infinity, since there are no charges here, the potential is zero on this southern hemisphere. The potential is as the radius r goes to infinity. And the potential is zero on the plane. Therefore, a solution that satisfies the Dirichlet boundary conditions, which says that there's no charge inside the region, so the first term is zero in the southern hemisphere. And if we choose Dirichlet boundary conditions, then phi and its derivative, or either one, is zero at this. And so it must be the case that phi of x is zero everywhere when I'm in the southern hemisphere. Okay? But now we want to solve this in the northern hemisphere with a bounding region at infinity. Okay, that's as we were discussing. So what I need to do is find a way of satisfying the boundary conditions. And anything that satisfies the boundary conditions and has only this charge in here will be a solution by uniqueness. So we can guess, in this case, a charge distribution that is different than the actual one, which is the surface charge that we know exists here, and instead guess using what's called the method of images. So let's just take the following problem. Two-point charges. Here's it's equals zero. There's no conductor now. Let me finish it up there. Okay. So if I write this problem, what is the potential everywhere in space? At all points of observation, given, so we have the image charge. It's the mirror image of this, and of course, in a bizarre world, I have the minus. What is the potential? So here I am at some position X, and I want to know what is the potential. What is the potential in that case?
Sum of the potential of two individuals.
That's right, which is what? What is the potential of a point charge?
Green's function.
We don't need a Green's function of point charge.
Q over R.
Q over R, right. And what is R?
Your position might.
Is the distance from here to here, right? So that is equal to Q over x squared plus y squared plus z minus d squared. That's for this charge. Everyone see that? That's what this script R plus is. And then what about the potential of this point charge?
Minus Q over the same thing by plus E.
Correct. Let's call this cylindrical distance S. All right, that's the distance from the z-axis in the xy plane. So, question, does this satisfy the boundary conditions? Yes. What is the potential at z equals 0? It's 0. So this satisfies the boundary conditions. In fact, if we draw the electric field associated with this, it's what we call an electric dipole. And if I only look in the northern hemisphere, it's this solution. Therefore, by putting the image charge over here, a point image charge, we have mocked up the effect of all the negative surface charge. It gives exactly the same electric field in the northern hemisphere as the point charge does. And instead of having to find this, we just guessed the solution. And by uniqueness, this is the solution in the northern hemisphere. It's not the solution in the southern hemisphere, but we don't care nothing about the solution in the southern. That's really common in life. But in this case, we really don't care about the solution in the southern hemisphere. We only care about the solution in the northern hemisphere. And so we can put whatever we want in the southern hemisphere, as long as it satisfies the boundary conditions, we're done. It's a beautiful method, and it doesn't always work, but when it does, man, that's easy. Okay? So that is the solution in the northern hemisphere, including the plane. So we've just solved it. Question. How would you find, well, yeah, so here's a question. How would you find what the actual surface charge density is? So I want to know what is the surface charge density on the plane. Sigma as a function of x and y. In this case, because of the azimuthal symmetry, it's only a function of s, the distance away from the z-axis.
Can you use that triangle for rho?
Yeah, when there's Steve, he's out there. We have this. So the surface charge density is determined by the boundary conditions. So we need to know what the normal component of the electric field is on the at the plane. And what is the normal component? Right, and the component is the z component, right? So what we have is that the is equal to the z component of the electric field as a function of s at z equals 0. Of course, that component we see is negative. This is in the negative z direction. And how would we find this, given this? The negative, the gradient, right? So this is equal to the negative, the gradient of this with respect to the z direction at that point. And that gives us what the charge density is. Yes?
So there would just be the partial derivative with respect to z.
Yeah, partial derivative with respect to z. And we're keeping s fixed. And then we look at this as a function of the radial distance. It's going to be, there's going to be a disk of charge that's going to fall off. Yes?
Do we have to be aware that there's an underside of that surface when we're calculating the charge? Like in this case, there's
Yeah.
nothing there, but there could be.
There is. However, if we have we do have to worry about that, but if we're talking about a conducting material, then the electric field is 0. So it's the difference in the electric field on the outside versus the inside that determines what the surface charge density is. And if we're talking about a conductor, on the other side it will be 0.
But what if we have another charge?
Well, then that would be a different problem. That's not the problem we're solving.
I'm
So
just saying, could we use this?
we could, but we have to, that would solve a different problem.
Along those lines, are we treating that plane as if there's two surfaces, the top surface and the bottom surface?
No, it's just, this is one plane. It's a plane of no thickness. I mean, if we had a finite, it wouldn't change anything on this, right? Because there would, in that case, what would happen is we bring in a certain amount of charge on each side, but the boundary conditions, we have to satisfy additional boundary conditions.
Would it be kind of like a Faraday cage? where
Exactly.
it's-
So that's what a Faraday cage is. A Faraday cage is if I'm having a place where I want to shield my system from stray electric fields, I can put it inside a conducting cage. Now, it doesn't have to be solid. I might have it be a cage, and it'd be pretty close as long as the fineness of my screen door is sufficiently fine compared to some other scales that the electric field doesn't leak in. So if I'm doing an experiment, as my friends in Sandia Lab are doing, with atoms that are excited to very high-lying orbitals and they're just waving out there in the wind and they're not bound very tightly to the nucleus, then there's a stray electric field, you're screwed. It's going to perturb it. So you put but kind of get your laser in to talk to the atom, so you don't have a solid piece of metal, you have a cage. All right, let's continue. So I guess, I'm sorry, yes?
What was the argument for why the potential is 0 in the southern hemisphere?
The reason is that it is the solution with the boundary conditions. The boundary conditions is at 0 on the plane and 0 at infinity.
Okay, so we set that as our boundary condition.
That is always the boundary condition.
Okay.
And if it's consistent. And there is one solution that satisfies that. Yeah.
Okay.
Yeah. So I want to say just one more word about the Green's function. Okay, what's the Green's function for this problem? Well, so as we said, we have a choice of how we choose f in a way, although we didn't calculate f, but we implicitly have f, which was the combination, in this case, well, I'll come back to this in a moment. Let me try to say the following things, which is that we generally choose the Green's function according to Dirichlet or Neumann boundary conditions. Okay, so let's come back to the first board here, where we had Green's theorem. Okay, now if I specify the system, let's look at Dirichlet boundary conditions. Which means I know this everywhere on the surface. Like what we just had before. We had a grounded plane and the northern hemisphere, and that, so we said that the potential was 0 everywhere there. So, but we don't care what the normal derivative is. We're not given that, and in fact, we can't have both. Can't have both ways. So, if we do that, it would be natural to choose the Green's function and thus implicitly choosing this F doohickey such that G equals 0 on S.
For S as a conductor.
No, this is not saying anything about a conductor. It's saying somehow, some way, I have some surface and I've specified what the potential is on that surface. Typically, that's most easily done by the conducting, but I might have, some thing that pins down what the potential is on the surface. This is a mathematical problem at the moment. But I have the freedom, because I have this F, I can choose it any way I want, as long as it satisfies Laplace's equation, to make this the boundary condition, in which case the potential everywhere would be given by So this is the solution. This is a perfectly valid solution to the Poisson equation given the Green's function that satisfies this. What it says is you convolve your given charge density with the Green's function associated with no potential on the surface, and add to it this contribution, which is effectively coming from the surface charge density associated with the additional potential that you've added. Okay? So now I ask you the following question. What is the Green's function with these conditions for this problem? I have a charge over here, or I have the following problem. So I have some rho of x somewhere over here, and I have this thing as, I'm gonna have some conducting surface which is a plane at z equals 0. And I want to know what is the Green's function for this problem if I'm interested in solving for the potential above this. So it means I can put any potential I want as a function of x and y on here, and I want to solve for what is the potential in the northern hemisphere given some charge density above the plane. How would I do it? Well, what I do is I first solve for what is the potential for a point charge somewhere. Doesn't matter where it is. And if I know what the potential is for a point charge, then I know it for anything, because the distribution is just the superposition of point charges, which is this, plus the induced surface charge density, which is here, because that's what this is. So now I ask you the following question. What is the Green's function? The Green's function is equal to the potential is the potential at x given point q equals 1 at x prime, that such that g as a function of x for x prime fixed is 0 on the surface, because that's what we chose. So if I know what the potential is associated with the point charge that I put somewhere that satisfies that the potential is 0 on the surface, that is the Green's functions for Dirichlet. Because I can get the total potential by just convolving, which is just superposing the effect of every dq at x prime, weighted by the solution, add them all up, plus the effect of the surface charge. And the effect of the surface charge is given by the normal derivative weighted by the strength of the potential there.
So effectively the two terms correlate to the two parts of the system.
That's right.
The rho
and then whatever surface charge. But you don't have to calculate the surface charge, you just have to do this. Once you solve the problem for the point charge with a 0 potential, you solve it for any potential. That's on the surface. Any boundary condition you had, that's the magic of the uniqueness theorem. God, we love that. So I ask you now, given what we've done, what is the Green's function for this problem? Well, we just solved it. It's the solution for a point charge above a plane that's grounded. Except now you set q equals to 1, and you set the point to be some arbitrary point, and you can write down the Green's function. And then you can write down the solution. If I put a battery here rather than a grounded with some plus or minus v, you'd solve that problem. You'd have an additional term. But we've solved for the Green's function because we've solved for a point charge that's grounded. So if you solve it for a grounded surface, or a point charge for a grounded surface, you've solved for the Green's function with Dirichlet boundary conditions. Yes?
So when you're saying we find a potential at some location x hat, that's just some any arbitrary location that we find convenient.
I'm sorry, I shouldn't make that noise. Can you repeat the question?
Right, bottom of that board
Yeah.
says Green's function is potential at x hat, or sorry, x arrow given, q equals 1 at x prime.
So here's my point charge, here's my point of observation,
Right.
and I want to find the Green's function. When I do, this is the problem of a point charge,
Right.
and we just solved it.
And both of those locations are completely arbitrary, whether.
They're completely arbitrary, except this one's above the plane.
Okay,
They're both above the plane.
because we're concerned with above the
We're
plane.
only asking what is this above the plane. We know what the solution is below the plane, it's 0.
Okay,
I mean, at least we're.
okay, so as long as we're within our spatial boundary,
Yeah.
it's arbitrary.
And if this was not, if this was, had a battery on it, we'd have to think more carefully about what the solution would be. But if we're only interested in the solution above, then we've already solved it. And the solution is here. But we have to think about, in this case, what script BR is, right? So this is equal to Q equals 1 divided by this one is mine. Yeah, that's fine. That's this.
Is E a unit vector?
Yeah. E sub something K is a unit vector along K. This is sort of the notation used in Jackson. And I always like this because I'm so used to quantum mechanics where hats are operators. So in this case, what I would do is I put the image charge over here, reflected to minus z, and that's what I just did, right? They're at the same radial distance, but they have the minus the z direction. That's the Green's function,
What's the equivalent of D here?
the z component of x prime. That's the distance that I am above the plane, is the z coordinate of where the charge is. Right? Yes?
So we solved it for a single charge and that's a Green's function with boundary conditions.
That's right.
But what we could do, we could solve it for free space, then add a f function, right?
Mhm.
That should be the same.
It will if the f function is the one that's coming from any, I mean, the f, at the end of the day, the solution has to satisfy the boundary conditions.
And so f depends on the boundary.
That's right. So, but we would have to know how to find f that satisfies that. There's no way to know it unless it's coming from other charges outside the region of interest. Right? So here the charges are coming from the surface themselves. The surface is not included in the region of interest. So you have to know what that is to get it right.
Also that boundary term,
Yeah.
dx delta a. So what you did was you you chose a Green's function such that one of the term is zero.
Yes, right.
So that's basically knowing one of the boundary conditions. Did you show that or no?
Right.
So you can put the other.
That's right. And if I had Neumann conditions, which is to say I knew what the electric field was everywhere on the surface, that is to say I know this, I would set its normal derivative everywhere to zero.
But if
I could also have pieces of one or the other.
But if I knew both, maybe I could not. do
No,
it.
you can't have both. You cannot specify both unless they're consistent. If you just arbitrarily chose them, it's not a consistent solution because of uniqueness. So in typical situations, what one has is one or the other or mixed. But at a given point, you can't just arbitrarily say, hey, I want this electric field and I want this potential. It won't be, it's not a physical solution. Yeah.
Even if you can't, yeah, okay, even if you can't arbitrarily pick them, we can.
There may be cases where they're consistent.
But we can find an equivalent case, like if, in the case that we have one, we can, solve for the potential and then potentially find a case where there are equivalent Neumann boundary conditions.
Yes, you
Yeah.
could have. Yes,
Yes.
there are equivalent. Yes, there are equivalent Neumann conditions that also solve exactly the same problem. But in a typical problem, well, the ones I'll never forget this one problem I had as a graduate student. I won't assign it to you, which is I have a beach ball, and every wedge I have a different potential. Find the potential inside. I think that was one of my least favorite problems. Okay. Now the method of images is one way to solve these things, but it's rarely, you can guess that kind of thing. We have to have other ways, and the typical ways that's done is by expanding in terms of orthogonal functions and using the separation of variables technique on the partial differential equation. And that's particularly true when, like the beach ball problem, when there are no charges, there's just the boundaries, then you're solving Laplace's equation with, so there is no charge, there's only something on the surfaces, and then you do an infinite series, satisfying the boundary conditions, and I hope you did those problems in 466, because we ain't doing them here. All right. There's one last thing I guess I wanted to say about conductors, and that is the idea of, actually, I'm going to skip that for now, and come back to that. This is something else I wanted to discuss. I mentioned when we wrote down this solution just by eye, that this is a field of a dipole. So an important, when solving electrostatics, in free space, without boundaries, often we are interested in asymptotic behavior. Okay, so I have some charge distribution that's localized within some region of space, let's say as a function of x prime. And I'm out here wanting to know this. And I'm at a position R, or a distance R, that's much, much bigger than R prime. For all the positions of the charge. So I'm very far away from the charge distribution. Its behavior tells me a lot. Okay? So what do we know about that? So let's just look at a couple of examples. I have a point charge. Let's say at the origin. Then the potential falls off like 1 over R. Okay. What if I have, as we just looked at over there, two equal and opposite point charges? Okay, so let's say I have a point charge plus Q and another point charge minus Q. Maybe it'd be easier for me to draw this on another board. So let's say I have 2 point charges of equal and opposite. Is that my hand?
It's not going away.
This is going to be like Lascaux, they're going to come back to the boards, you know, these ancient people use chalk. Yeah. Anyway, so here's plus Q, here's minus Q, and there's some distance between them, D. Okay, let's put the origin right between the two. And here I am at some distance from the origin. And I want to know what is the electrostatic potential associated with these two. Right, so there's some distance, some vector, I'll call it R plus, which is the distance from the positive charge to B. And there's some, they're supposed to be at the same point, excuse me. Anyway,
Didn't we just solve this one?
you did. So let's just, what I want to do is ask you asymptotically far away. Let's say the distance between these guys is D. And if I want to say that R is much, much, much bigger than D. So I'm very far away compared to the size of this distribution. What the lowest non-vanishing order is the potential? Well, we know the exact, right? The potential at X, I want to call this X, is equal to Q over R plus minus Q over R minus, right? Which is equal to Q R minus R plus over R plus times R minus. Okay? So what's the difference in the distance between these two guys? Let's say that let's use this angle theta. Then, you know, like you do with the double slit experiment, you can say what's the difference in the path length when I'm very far away. It's basically this distance, right? If this is theta, then this is theta. This is confusing. This is theta. Right. So this is d cosine theta. So this distance here, so this is d cos theta. And to lowest order in R, this is the same as R squared. Little r squared.
Where are you
And times q. That is approximately to lowest order. We'll do a more formal expression in a moment. There are corrections to this that go like 1 over r to the third, 1 over r to the fourth, etc. So, the thing I want you to notice about this is the following. For the point charge that had total charge Q, the potential fell off like 1 over r. Goes to 0, but it goes off relatively slowly, falling off with distance like 1 over r. Whereas when we have two equal and opposite things, this is a neutral charge distribution, the total charge is 0. In this case, the potential falls off much more rapidly. Yeah.
Which element was d cosine theta?
Well, this distance, this difference,
Okay.
right? That's the difference between this length and this length in the asymptotic limit. But importantly, again, the thing I want you to focus on is the fact that the potential falls off much more rapidly, and it falls off like 1 over r squared in this case. If I had this problem, let's say I'm going to now, this is called an electric dipole. We'll come back to that. What do you expect in this case? I mean, it's neutral again, so it's going to fall off faster than 1 over r. But it's also, if I look at this, it's kind of the two dipole moments are opposite. And they're canceling. There is, as we will see, there is no dipole moment in this case. In this case, we have a quadrupole. And we can do the same problem in this case. It's in the notes. I'm not going to do the algebra here. Let's say, I'll just put some coordinates on here. In this case, what we find is that the potential as a function of position is equal to let's say in the xy plane is equal to 12 xy q d squared over r to the fifth. No, yeah, that's right. Which is proportional to 1 over r to the third power. Why is it proportional to 1 over r to the third power? Because x and y are proportional to r, right? X is equal to r cosine theta sine phi, y is r. So the farther away I am, x and y are proportional to r. This goes like 1 over r to 5. So this whole thing falls off like 1 over r to the third. Notice, falls off like what the guy that had a monopole, a charge that we called a monopole and a definite charge, the potential fell off like 1 over r. If we had something that was neutral, had no monopole moment, but had a finite dipole moment, it fell off like 1 over r squared. In this case, the lowest non-vanishing moment, as we will see, is quadrupole. So it falls off even faster with distance. It falls off like 1 over r cubed. This kind of power series is going to be very important. These moments, as we call it, are called multipole moments, and they allow us to characterize our charge distribution. If we know what the moments are of the distribution, then we know what the potential is far away. Without solving Green's functions or anything else, we can, as we will see, the asymptotic properties, what the fields look like far away from distribution is determined by their moments.
We're looking at multiple expansion?
We are, that's what we're gonna do next, but I just wanna say one last thing. So the potential far from a charge distribution is determined by its multipole moments. Let me just do one quick last example in my grace period of 3 minutes. Let's say I have a ring of charge that's on a circular ring in the xy plane. It has a total charge distributed everywhere along this line, okay? And I ask you, what is the potential on the z-axis? Exactly, what is the exact expression for the potential? So it's a ring. Well, I have to add up the contribution from every point on the ring. The distance from here to here contributes that of a point charge, and they add them all up. However, everyone is the same distance on this cone. Every point on this ring is the same distance to that. So they all add up together. And the potential on the z-axis would be q over script dr. But script dr is equal to the square root of z squared plus a squared by my friend Pythagoras. You with me? So now I want to know, what is the potential far from when I'm on, as z goes to infinity, when z is much bigger than the ring? So in the limit, as z is much, much bigger than a, well, it just q over z, I don't really see it. It's approximately this, which is what you would expect. I don't really care what the size is. It looks like a point charge. If I can't see the fact that it's a ring, it's a point, right? However, I can ask, what's the first order corrections to this? How would you do that? This is something, if you don't come out of anything from this class, I want you to be able to do this, which is to do an approximation in your head on the binomial, using the binomial theorem. So this is equal to, when we want to look at this limit, what this is saying is that a over z is much, much less than 1. Okay? So when you do an expansion, the first thing you do is say, what is the small parameter? This is the small parameter, because we're going to take the limit as z goes to infinity, and thus this goes to 0. So I'm going to rewrite this by factoring out A, and write this as 1 plus, I'm sorry, factor out Z, A squared over Z squared to the minus 1/2 power. You see what I did? Okay, so when this goes to 0, I can forget it's that, but I can do the first order correction. And what is the first order correction?
1 minus A2 over Z2 times
To
2.
to the over 1/2, right? So here, everyone needs to remember this. 1 plus n, 1 plus x to the power n is approximately 1 plus n times x, when x. Everyone know that? Use it.
That's the binomial limit,
Yeah.
you said, binomial limit?
Yeah, but I mean, it's the first order. Everyone you have to know that. And so what is this then in the limit, first order? Is what we said. This is q over z times 1 minus 1/2 a squared over z squared, which is equal to q over z. This is approximately equal to minus 1/2 q a squared over z cubed. So that's a quadrupole contribution. The dominant term is the monopole, but this distribution also has a quadrupole. We'll understand that a little bit more deeply next time. This is a quadrupole correction. We could then, there will be this of course, I can do a power series expansion and get the other moment contributions. When I get far enough away, the quadrupole falls off much more rapidly than the monopole will dominate. The lowest non-vanishing moment dominates when I'm very far away, but there will be corrections due to the higher order moments of the distribution. Yes?
When you do the quadrupole on top,
Yeah.
you do 4 in that, what kind of classic quadrupole?
Yeah.
But if I took them and put them on top of each other, that's still be a quadrupole.
It wouldn't have, no, it would have a octopole actually. Yeah, we'll do it. That's a pole. All right, I've kept you long enough. I'm taking off. Have a good rest of your day. Don't forget to pick up your homeworks on the way out.